Okay, a couple of announcements before we get started for today. Sorry, it looks like the materials that were originally planned for this unit were not available when I thought they were. So while your syllabus said Mastering NP Chapter 7 was due today, obviously it's not your fault that you can get into that. So go ahead and do that over the weekend. So turn those in Monday night. That said, we are going to move into talking about neurons. Okay. What I want you to know about the membrane potential of neurons, there's a lot of information in your textbooks about the setup of a neuron and how we get to our membrane potential for a neuron. But what I want you to actually know is the actual situation in the body when we have an existing neuron. So to that point, our end goal is really just to understand the resting potential of a neuron when we get started to think about how cell signaling happens. So we should remember from last time, we'll do a little review here, right? So when we have a cell has a membrane potential inside of it. So that's the VM. So we can think of that as like the volts on the membrane. And I used -70 as our example throughout the last unit because that is going to be the resting membrane potential for our neurons, okay? That's why we kept talking about that one specifically. So might as well practice as we intend to go on. So that means that relative to the outside of the cell, the inside of the cell has a charge of -70 millivolts. That's what this means. So when we're thinking about a neuron, we're thinking about our starting point on the inside as -70 millivolts. The reason I keep repeating that is that as we start to talk about signaling between our neurons, we're going to see that the signal actually is a change in that membrane potential. When we think about our neurons as like zapping each other with electricity and sending signals through our body that way, what we're talking about is changes to the membrane potential. So that's why we're starting here by understanding the cell at rest. Okay. So at rest, our resting membrane potential is at -70. And the things we want to know about why that is really the main things that we're going to be paying attention to when we talk about neurons. For two of our ions, we're going to be thinking about sodium and potassium extensively. Okay. So relative to those two ions, right, our equilibrium potential for sodium is positive 60, meaning that if we get the cell up to positive 60, we change that membrane potential all the way up past 0, we happen to get to positive 60, that's when sodium would no longer want to move in any particular direction. We'd have equilibrium, we'd have net movement in one direction versus the other. Our chemical driving force and our electrical driving force would cancel each other out. That is what our equilibrium potential means, right? So for sodium, that happens if this cell gets to positive 60. For potassium, same thing, we have an equilibrium potential for potassium. It's different than our equilibrium potential for sodium. It's negative 94. So way at the opposite end, right? So for potassium, potassium is going to want to move to get that cell to negative 94 millivolts. And that is when potassium is going to have equal and opposing chemical driving forces and electrical driving forces. So potassium will stop moving. So we can note on this scale that the resting membrane potential is negative 70 millivolts. So it's much closer to that potassium equilibrium potential. The reason for this has to do with this membrane and the proteins in it, right? So what we're going to see when we look at that membrane, I'm gonna pick, let's do red for sodium. Okay, so we're going to have some sodium channels allowing sodium to move. All right, so here's a sodium channel. And we're going to have some potassium channels. I'm going to draw 3 of them. So 1, 2, 3 in purple. All right, just to illustrate. So these are our potassium. And these are our sodium channels, which means that sodium can get into the cell, right, if it wants. So sodium is going to want to move into the cell because it's trying to change that negative 70 to positive 60, right? So if we get one sodium, say we get to negative 69, another sodium, negative 68, and so on until we get to positive 60. So it wants to move in, but it only has like one doorway to do that, right? So the membrane is permeable to sodium because of this channel, but it's not very permeable. You can just think of it as just having one of these channels versus potassium. Our membrane is much more permeable to potassium because we have more potassium channels. And potassium is trying to get us to negative 94. So it's pulling the opposite way. It's still a positive ion, but we can make this cell more negative by removing positive ions. So you remove a positive charge, get down to negative 71, remove another positive charge, negative 72, and so on. And because potassium has a greater ability to move, because this membrane is more permeable to potassium, like there are more potassium channels, that means we're going to come down much closer to that membrane potential, right? So potassium is kind of winning because of that greater membrane permeability. A thing that is also true at the same time is that because sodium is so far from that resting membrane potential, sodium really wants to move in. There's going to be like a strong force for sodium to move in, right? So it really, really has like a far way to go. So if we open up channels, we're going to see a really fast movement of sodium because of that distance versus the force for our potassium, because we are closer to that equilibrium potential to start with. There's a little bit less of a force for potassium. So potassium is moving, but it doesn't have so much motivation because we're closer to where it wants to be. If anything in the rest of today gets confusing as we briefly go through the setup, this is really what I want you to know and understand and get to. The questions at this point. This is what's going to set us up for our actual cell signal. As the most important portion of this. So here we can see some of this setup, right? So this is just a different view from your textbook, right? So here we see a sodium channel, and here we see some potassium channels. Right? So this is essentially what I was drawing before. But now we can see a little bit of what's going on to set that up. So we can see that part of the reason for this movement is a chemical gradient, right? So our potassium are here in this bluish purple color, right? So we have a higher concentration of potassium inside the cell versus outside the cell. Or we could look at the sodiums. Part of the reason they want to come in is because of that concentration gradient as well. The reds are our sodium, lots of them outside, not very many of them inside. So that's part of why it wants to come into the cell. And part of the reason that the state is maintained, right? Because we have these channels, our ions are moving through these channels. We just let them move and move and move. This -70 would change, right? As we have some sodium coming in, as we have potassium going out. But we also have a sodium potassium pump, right? So this sodium potassium pump sends 3 sodium out by primary active transport, pulls 2 potassium in. So it's maintaining this high potassium inside. And it's maintaining that high sodium outside as it's moving those in opposite directions. And because it doesn't move them equally, so the sodium potassium pump is actually moving 3 sodium out, 2 potassium in. So sometimes you'll see it referred to as an electrogenic pump, meaning it's moving more charges out than it's moving charges in, right? We have positive ions, but we're taking 3 positive charges out, only bringing 2 positive charges in. So it keeps us more kind of in this negative range for that reason as well. So when we think about our proteins in the membrane that are important for this membrane potential, we're thinking about our ion channels. We'll later, I think, refer to these kind of as leak channels. So these are our ion channels. We'll talk about the different types of ion channels as we move through the neurons. All right, but we have sodium ion channels and potassium ion channels. And we have a sodium potassium pump that uses energy in the form of ATP to maintain this at a steady state. So the rest of these slides go through the portion of your textbook that tells you like how we get from a fake imaginary cell with no charge to this final resting membrane potential. So the real thing that I want you to know is the final basis, but looking briefly at the setup may or may not sort of help you understand why it is that way. Okay. So we're starting with a cell with a sodium potassium pump, right? We'll draw our pump and we can use red, okay? All right. So we're moving 3 sodium out and we're moving 2 potassium in. And as we do this, right, say we start at 0 millivolts. And imagine we run this once, right? subtract 3 positive charges, add 2 positive charges, right? So let's say we're now going to go down to -1 because we lost a charge, run it again down to -2, and so on, right? So this sodium potassium pump is lowering the membrane potential, lowering that charge. So that's like the first step of setting up this negative membrane potential. Now we have to, this is just a reminder about these equilibrium potentials for the potassium ions and the sodium ions, which are partially due to existing concentration gradients around the cell and inside the cell. That's why they're different for different ions. And that sodium potassium pump is part of what sets up those chemical concentration gradients, right? So we remember that our electrochemical driving force is adding together the chemical driving force, electrical driving force. So both of them matter for the equilibrium potential, because our equilibrium potential is just when our electrochemical driving force equals 0. So electrochemical driving force equals 0, and our CDF and our EDF are in opposite directions. So equal and opposite. Our resting membrane potential exists because we end up with, on net, more negative charges inside the cell, more positive charges outside the cell. Cells have negative resting membrane potentials normally. For our neurons, which is what we're thinking about, they're at -70. Okay. So part of this is due to ion concentration gradients. Part of it's due to the membrane permeability of those ions, aka those numbers of ion channels that we just looked at. So this is just a sort of reminder slide about some words. I wouldn't focus too much on memorizing any of this. So our sodium potassium pump is partially responsible for our resting membrane potential of -70. 20% of it is like directly the responsibility of the sodium potassium pump. That's the Na+, K+, ATP ACE. That's just another way to phrase our sodium potassium pump. ATP ACE tells us this primary axis, and we're using ATP. So that 20% is just talking about the part where we're moving more positive charges out, right? For sodiums, moving fewer positive charges in, the 2 potassiums. So we're net exporting a charge. Then the rest of that resting membrane potential is even more negative because we produce concentration gradients, lots of sodium on the outside, not very much sodium on the inside because we've been taking it all and pushing it out. Potassium, low on the outside because we've been pulling it in, making the inside of the cell higher in potassium. So our typical neuron, permeable to both of them, both potassium and sodium, actually 25 times more permeable to potassium. So I could have drawn on 25 little potassium channels there, but that would have taken a while and gotten messier. So it's a lot more permeable to potassium, right? Not just a little bit. If we're thinking about the actual ions in the cell, right, we're going to focus on the sodium and potassium part, but there are other things happening, right? So outside sodium and its buddy chloride ions, potassium on the inside, and some organic anions. So I'm just going to write question mark negative, right? So some organic things. Okay. So here we're separating out just the chemical driving force for the potassium, right? So our chemical driving force for the potassium is out because we have high potassium inside, and we have low potassium outside. In this case, we didn't even see any drawn on here, right? So our CDF is out. And because we have a membrane potential of 0 on this cell, because this is like our starter cell, there's no electrical driving force at all. So that CDF is the whole sum of the forces. As we move those potassium ions down their gradient, so from high to low, now we start to see that we have changed the potassium ion gradient, still high to low, but a little less of a difference. But because we've been moving positive charges out, the inside of the cell is now negative. So we have a growing electrical force as positive charges are drawn towards negative charges, right? Opposite charges attract, right? So the charge, that negative charge inside the cell, is attracting those positive cations, the potassium ions from outside the cell. The concentration gradient is still winning, right? So our CDF is still bigger here, right? We're not at the equilibrium potential for potassium, but now once the inside of the cell is negative, we do have an EDF as well, right? Eventually, we could reach equilibrium if nothing else was going on. So by definition, at equilibrium for potassium, we have equal and opposite CDF and EDF, right? CDF here, EDF here, meaning that the pull into the cell from this charge, this -94, is equal to the push out of the cell from this difference in concentration of potassium. So the electrical force opposes the chemical force. They're opposite in direction and equal in magnitude. So that's an explanation about what's true at the equilibrium potential.
They stop moving or they move at the same rate?
They would move at the same rate, essentially. Yeah. Equilibrium is when there's no net force, right? We still have random movement because there's random movement all over the world all the time. So the chemical force equal to the opposite of the electrical force. Electrochemical force, 0. We're going to look at another hypothetical cell only for sodium, and we're going to see the same sort of situation, but we're starting out with the opposite concentration gradient. Okay, so now we're starting with our sodium concentration. So high sodium outside, low sodium inside. So sodium is going to want to move into the cell. And in this imaginary cell, we started at 0 millivolts. As the inside of the cell becomes more positive, like charges repel each other, right? So sodium is positive. Sodium is positive if the inside of the cell is positive, right? They're bouncing away from each other, right? Because they're the same, which means that sodium is being pushed out of the cell by the EDF, okay? So as the cell becomes positive, the EDF points out until it reaches its own equilibrium. And that's how it would get to positive 60. We're actually not going to see our ions getting to their equilibrium potential in our cells. So this is only a sort of hypothetical situation. This is where it's trying to get to, though. Okay. So the chemical force on the sodium is to move in. The electrical force is to move out at the equilibrium potential, which is positive. So for the resting membrane potential, we just add these together. We have a potassium force out, right? So potassium as a chemical force out, sodium as a chemical force in, okay? And that is important to remember, those directions for our neurons, right? Sodium is going to want to come in, potassium is going to want to go out. That's a really important thing to remember as we continue to talk about neurons. That's our setup here. So that was true on our first slide as well when we were looking at the existing membrane potential. Okay. So membrane is more permeable to the potassium, right? 25 times more, in fact.
So more potassium is leaving the cell. So the inside of the cell is becoming negative, even though we have some sodium coming in. Right? Sodium wants to come in, a little bit of sodium does come in, cell stays very negative because lots of potassium is moving out. So electrical forces are now developing. And in this case, we see a different thing than when we were going through our imaginary cell just tracing sodium, right? So in this case, our chemical force for sodium, high to low, right? So our CDF is in. But when we went through our imaginary sodium cell, our inside of the cell was becoming more positive. But actually, because we've now added on the potassium, the inside of the cell is becoming negative, right? Because we have lots of potassium flowing out. So our electrical driving force for sodium is also in, right? So both the chemical concentration and that electrical force point in. So this is part of why sodium really wants to rush into a neuron. There's nothing stopping sodium from coming into that cell except for the fact that it can't get through the membrane, right? Chemical driving force wants it to go in, electrical driving force wants it to go in. So we would have a really big arrow if we add them together for our electrochemical driving force. Not so for the potassium, right? The potassium has been going out. Now it's attracted to that negative. So we have opposite directions for our potassium. So our electrochemical driving force, the chemical force is bigger than the electrical force, but we'd have a relatively small electrochemical driving force out. I'm emphasizing the strength of this force on the sodium because when we talk about action potentials, which is how neurons signal to each other, we're going to see that there's a point in time when we let sodium into the cell, when we make that membrane more permeable to sodium, and sodium is just going to flood in because of this strong force. Okay. So when we're at the steady state, everything's kind of balancing out. That is at -70. And then that sodium potassium pump is keeping us stable at this state. Here's that illustration from the first slide, right, showing us that we are much closer to our equilibrium potential for potassium than we are from our equilibrium potential for sodium. Right, so potassium is really keeping us down. Potassium is kind of driving this negative charge, this negative resting membrane potential because the cell is so permeable to potassium at the moment. So if the membrane potential is not at the equilibrium potential for an ion, the electrochemical force is not zero, means there is a force on it. We're going to be moving in the direction that takes us closer to the equilibrium potential, right? If we're really far away from the equilibrium potential, right? So like our +60 equilibrium potential for sodium, really far away from the -70 resting membrane potential, right? We're going to have a strong net force versus our equilibrium potential of potassium at -94, decently close to the -70 membrane resting membrane potential of this cell. So that's a slightly weaker force. So resting membrane potential close to potassium. We have a slight electrical force into the cell because negative charges attract the potassium, but we have a strong chemical force pointing out of the cell because of the high concentration of potassium inside the cell and the low potassium concentration outside the cell, which we've set up with our sodium potassium pump. So this is a pretty weak force versus our sodium, right? If we did the math, we'd have to come up 70 to 0, then add 60 more. So we're 130 millivolts away from our sodium equilibrium potential. The electrical and chemical forces both point into the cell. So we have a really strong net force for sodium. We have a strong electrochemical driving force on the sodium, but we can't move the sodium until we make the membrane permeable to sodium. So low permeability is why we don't see a lot of sodium movement. So we only have a little bit of sodium moving when we're at the resting membrane potential, right? So we have the high force referring to that ECDF is high, and that's our chemical driving force, plus our electrical driving force. They're going in the same direction. So we have a really high force, but we have low permeability because we don't have any channels. Right? Not enough channels. That's what our low permeability means in practical terms for us today. Opposite situation happening for potassium. A little bit of potassium leaks out of the cell because our total force or the potassium is out of the cell, but it's not rushing out because we're pretty close to its equilibrium potential. We do have a high permeability to potassium though. We can take a look at what this looks like.
The human brain alone contains about 100 billion nerve cells, all neurons. A neuron, like every other cell, has positively and negatively charged ions inside and outside. Further, a resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. Distribution of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter. On average, an intracellular electrode records a value of -70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential properties of the plasma membrane to sodium and potassium ions. These channels in the plasma membrane are demonstrated in the energy to the heat down their concentration gradient. The membrane contains many more potassium-rich channels than sodium-rich channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions reach out the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface. The roots help to maintain the resting membrane potential.
So this is another sort of explanation for where we're going. So why we're talking about this is that when we talk about signaling with neurons, when we refer to an action potential, the action potential is like a pulse down the neuron. It's actually an electric pulse, right? So it's a charge that's running down the neuron, essentially, right? So it's always going to have a really characteristic shape. right? So over time, right, for any given little segment of the neuron, we're going to start at our resting membrane potential. We're going to have some fluctuation of charges as things happen to the cell, as signals come into the cell. We're going to be able to add together those little changes to the resting membrane potential. And they don't do much of anything unless we get to -55. So like, I'm going to draw something else over here, just real quick. So if we had the same sort of thing, time and membrane potential, and we'll have -70, -55. Draw those blue lines, right? Okay. So what we're going to have happening is that we're going to start at -70. Sometimes signals are going to come into the cell, right? It'll change the charge a little, and then it'll go back to the membrane potential. Maybe we go down, come back to the resting membrane potential, and so on. None of this sends a charge down the cell. But if we have enough signals coming in that we end up over -55, suddenly have this spike, right? So this hitting this threshold of -55 essentially is going to cause a lot of sodium to be able to come into the cell. So we have this spike, and that spike rushes down the neuron, which is actually not a little circular cell. It has like a long branch. And that is the signal that we're sending to other neurons. So it has these sort of steps as we're getting up to that threshold, right? So this is before we send off the signal. Then once we hit it, we can talk about what's going on in this first phase as we spike up. You can see we get to a positive state, but not always all the way up to our positive 60 equilibrium potential for sodium. Then we're going to have a second phase. When we come back down, we're actually going to overshoot the resting membrane potential. And then we're going to repolarize, get back to -70. So the reason we're talking about these forces for sodium, for potassium, and where our membrane potential is at rest is so that we can figure out why this happens, when this happens, how this happens. So as we start to talk about that, I do want us to be able to cue into like where on a neuron we are, because we're going to be talking about the signal moving down the cell. So it's important to realize that a neuron doesn't look the same as our like little fake round cell, right? Actually, when you look at cells on slides in your histology unit, you'll see that there are a lot of cells that are not small and round. They have a lot of different shapes. Here is an example of a stereotypical neuron. So there are different types, and some other ones do have different shapes, but this is like going to be our basic neuron. Okay. So when we talk about the soma of the neuron, we are talking about like this central part. So soma means body. And I'm telling you that because later we're going to talk about like somatic nerves, which are going to go to muscles, versus autonomic nerves, which are going to do different stuff. So this root soma will show up again. So the soma is this sort of body part of the neuron where we have our nucleus and we'd have our organelles, right? So say we have a mitochondria, I don't know, maybe we have some Golgi, you know, all the typical stuff that we have inside a cell would be in the soma. We're going to have some little branches coming in to this soma, to this body, and they're sending signals essentially from other neurons. So you'd have another one sort of here, right? So another soma, right? And more dendrites, right? So they're going to be like in a chain, essentially. So those are the dendrites. The dendrites, I think this comes from some Greek word for branches or trees or something. And Greek's not very good. So the dendrites are for incoming signals, right? So incoming. And then the place where we send signals is the axon, right? So the axon would be this long skinny part. Like, let's say from here to about here. That's our axon. So this is where we're going to be talking about that wave of charges, right? So we're going to see that peak first here, then it would be here, then it would be here, and so on. So it's going to travel down that axon to the next cell in the chain. And on either end of that axon, we can also talk about some regions. So the axon hillock is a hill coming to the axon. Okay, so that's this hill, like this triangle-ish shape that I'm highlighting. The reason we care about the axon hillock is that it's this region where we care most about the threshold. So it's really if this region hits -55. All right, so that's our threshold. And we will talk more about this threshold and the action potential in detail. All right, so it's that region in the axon hillock where we're thinking about, do we get to this threshold? Because if so, we're going to send this peak of charges down the axon. And then at the axon terminal, where we connect out to our next cell, right? I have another neuron over here. All right. These are our axon terminals, so terminal termination. So each of these is an axon terminal, essentially. All right, so these little fingers are the axon terminals. This is where we release our neurotransmitters. So our neurotransmitters, when you talk about like brain chemicals, brain chemistry, any meds are often related to neurotransmitters, right, for mental health conditions, right? So we're talking about neurotransmitters that are initially stored here in the axon terminal. So they're going to be in little baggies, little vesicles in the axon terminal. When this charge, that action potential, that peak reaches the end of the neuron, that's a signal for your cell to take these neurotransmitters, put them out through exocytosis, right? So we're just taking that little vesicle, merging it into the membrane here of the axon terminal. We release the neuron transmitter into what we call a synapse, which would just be another neuron, right, reaching, getting a signal in essentially, right? So the synapse is this sort of central gap part. We are going to talk about all these pieces, right? We're going to talk about how this is happening and why this is happening. But understanding, or at least having like an overview of the big picture first, can kind of be helpful for predicting why we're talking about something and what that's going to mean for an actual person in front of you. All right, so we're going to go ahead and think about something called depolarization. So this is going to be one of our vocab terms for future lectures. So depolarization, okay, depolarization can happen if we open sodium channels in a cell, right? So let's say we have a neuron, make us a neuron like this. I'm not going to, we can draw on the dendrites, right? So we have a neuron. It's going to have an axon terminal. It releases some neurotransmitters. And our next neuron receives it. I'll just draw the soma here and imply that it's going, right? So what we're saying is that we've opened more sodium channels when this neurotransmitter binds on, right? So let's say we had some closed neuron channel, closed ion channels. We have this neurotransmitter bind on and open them. So now we have more sodium channels. We still have our potassium channels that we had before, but they're not affected, right? So let's say we still have those 3 potassium channels that we've been drawing on. So I want you to think about what effect this has on the overall membrane potential of this second cell in line. Okay. I want you to think about what would happen if the potassium channel opened. All right, so let's say we opened more potassium channels. Sodium versus potassium. So who wants to tell me what you think would happen if our neurotransmitter causes a sodium channel to open? What's that going to happen? What's going to happen to that resting membrane potential? Say that again. Yeah, exactly. Right. So in our little imaginary cells we've been drawing, right, we've been saying that both the CDF and the EDF for sodium are in. Sodium really wants to move in. So we're going to have more sodiums moving in. Sodium is positive. So this is going to make the membrane more positive. So the membrane potential is going to go up. Right? So we're going to go from like -70 to, let's say we get to -65 or something, right? So this is a possible thing that could happen if we have some sodium channels open. So that is depolarization. That's what this word means. If we say something depolarizes, when we're talking about the polarity of the cell, we're really talking about that difference in charge across the membrane. So we're talking about the fact that like -70 is not 0, right? So this is the polarity of the cell, is that negativity, right? So when we depolarize, we're getting closer to 0 here, right? So we're depolarizing the cell, making it more positive. So what's going to happen if we do the reverse, if we open a potassium channel instead? I'm thinking about potassium. So what direction does potassium want to move? Yeah, so potassium wants to move out, right? So potassium moves out of the cell. And that's because the chemical driving force is stronger, right? So we had high potassium inside. We had low potassium outside because that sodium potassium pump is messing with our gradients, right? It's pulling potassium into the cell. So we want potassium to move out. So if we move a positive charge out, what is happening to that membrane potential? Is it going up or down if we move a positive charge out? Yeah, exactly. Not a trick question, right? So if our neurotransmitter causes some potassium channels to move out, we're going to become more negative. Or negative. And this is called hyperpolarization. Right, so we're getting farther away from zero, so we're hyperpolarizing, hyper more. So this is going to set the stage for what we do next time as we start to talk about how we get to that -55 threshold and set off an action.